This will be a quick video with a single problem solution. This problem, number 74, is listed among the challenge problems at the end of chapter 10, and it's not part of your homework, but it's an interesting one. We've got a hemispherical slide. Maybe you've seen something like this at a playground. It's just a big dome, and the surface is smooth, so if you sit at the top, you could slide off of it. And as I've drawn it, it's a little too big, right? If you were sliding from this high, you might actually injure yourself. So it's not really to scale. I'll use the letter capital R for the radius of this hemisphere. And the problem asks us to determine what is the angle at which this person will slip off of the surface. You probably have some intuition that you're not going to make it all the way to the ground before your butt detaches from the surface. So if you draw a line from the center of the hemisphere to the person, how far down do they get? At what angle would they slip off of the surface? And in order to solve this problem, we'll have to combine the conservation of energy equation, which we've been dealing with in this chapter, and some of the circular motion dynamics from earlier, chapter 8. So as always, if you don't know how to proceed, just write down the few equations that you do know. Let's start with this one. Work total is delta K. I'm going through all the steps here. That's work done by gravity plus work done by a spring plus work done by non-conservative forces, and that's got to equal change in kinetic energy. This comes from F equals ma. In this problem, I see no spring forces, and we've seen now that the work done by gravity can be thought of instead as the negative of the change in gravitational energy. And as far as any non-conservative forces, I really only see two forces here. I've got the normal force pushing up on this person, and then the gravitational force. Also note that if this is phi, this has to be phi as well. But the person always slides tangent to the hemisphere. Their instantaneous velocity is always tangent, which is perpendicular to the normal force. And remember, two vectors are perpendicular, their dot product is 0. So a perpendicular force cannot do work on an object. Perpendicular to the velocity, that is, instantaneous velocity. So really there's no other work being done here. And we're really saying that U is equal to delta K plus, that 0 is equal to delta K plus delta U. This is just another way of saying that the total energy stays constant, right? The change in total energy is 0. Where total energy is the sum of kinetic energy and potential energy. So we could say also that E initial equals E final. And you could have started here if you were confident that it was appropriate to start here. You kind of have to establish first that there is no work being done by non-conservative forces. Okay, so let me label some times here. TI for T initial, that would be begin sliding at top, and T final will be the time at which we leave the surface. Okay, well, before we can apply the formula for potential energy, we have to choose a coordinate system. You always have to do that first. Let's go with up as positive. Again, my advice is if you're going to do a problem involving the formula for gravitational energy, call up positive. That's the smart choice, the easy choice. Let's put the origin down here. The physical result of the problem, the solution you arrive at, does not depend on where you put the origin. It's just the algebra that might look a little different at first. But it doesn't matter if you say this is 0 or this is 0 as long as you're consistent. Okay. So energy initial, well, that would be K initial plus UG initial, K final plus UG final. Can we cross anything out? Very often one or more of these terms is 0. Well, we start, presumably this kid, I'm going to say it's a kid sliding down here, they start from rest. They have no kinetic energy. They just barely push off from the top and start to speed up on the way down. So no initial kinetic energy. Now, I'll go ahead and write all the steps here. mgy initial. That's my formula for potential energy. I can only use that formula if I've decided to say that the potential energy here is 0, and if the gravitational field is constant. So I'm just rehashing the assumptions that go into that. But until chapter 13, it's safe to use this formula for gravitational potential energy. As long as you keep in mind, this is the potential energy over and above what you would have down here. Okay, 1/2 mv final squared plus, well, what is the final y coordinate? Okay, now we're going to have to do some trigonometry. Well, before I actually evaluate that, I'll just write mgy final. Okay, what the equation says is the potential energy that you start out with is transformed partially into kinetic energy on the way down, and then the remainder is still potential. So let's continue here. If I look at the diagram, I can see that the initial y coordinate is just the radius r. That's how high they are above the ground. So I'm going to substitute r here. And do you notice that there's an m in each term? So we can divide out the m's, and I wind up with rg equals 1/2 mv final squared plus, and what's left here? Well, the y final. Let's extend this segment here. I don't know what that angle is, but I'm calling it phi. At some angle phi, this person will detach, or the kid will detach from the slide. So we need the y coordinate right there. That would be this side of a right triangle. See this right triangle here? We need this side. So take the hypotenuse, which you'll notice is also the radius of curvature, multiply r by the cosine of phi to get the adjacent side. So the height at this particular coordinate would be r cos phi. I believe I've done that right. Remember, whoops, I was about to say that the m's are gone, but I forgot to divide out that one. Okay, well, let's solve this for v final squared, because I know from having done this problem that we're going to need that expression. V final squared would be, now do you see that this term and this term both have an rg in common? So I could factor out that rg, and I'd have 1 minus cos phi, and then I'd have to multiply by 2. So there it is. And so we don't get lost in the thought process here. There is some particular time corresponding to a particular angle at which this kid is going to lift off the slide. I'm calling that time t final. And this angle phi, that's the angle that this line would make, the line from the center to their body. That's the angle that line makes with the vertical at that time. And I've used conservation of energy to express the speed of the kid in terms of that angle and the radius of the hemispherical slide. That's required by conservation of energy because there's no other force doing work here. It's just gravity. There's no friction that's been mentioned. There's no air drag. So this must be true, provided that they're constrained to move on the surface. Once they lift off the surface, you wouldn't be able to apply this condition. But as long as they're moving down the slide and stuck to it, as long as their butt is stuck to the slide, this has to be true because it comes from F equals ma, ultimately. So if that's not true, then F equals ma is not true. Okay, now v squared. Hopefully you're thinking, wait a minute, I've seen that before, v squared over r. That shows up in the dynamics of circular motion. So let's see what else we can determine. We've already used our conservation of energy equation. Let's go back to the dynamics of circular motion because this person is moving in a circle until the moment when they leave that circle. So we'll say some of the forces in the r direction is mass times the so-called centripetal acceleration. I'm applying F equals ma along the r axis. And remember, the positive axis, or the positive direction, points towards the center. Okay, remember, there is no friction. Even if there were, it would be tangential. I only see two forces, the normal force and this component of gravity. Gravity points straight down, but I've resolved it into components, one of which is along the r-axis, and the other would be along the t-axis, right? T-axis is right here. Okay, which one gets the plus sign? Your book uses plus for any forces that are towards the center. So this is mg. Multiply mg by cos theta to get this. Mg cos phi is what I've been calling it, minus the normal force equals, and now we have some options here. Remember, there were 3 equivalent formulas for centripetal acceleration. There's v squared over r, there's r omega squared, and there's 4 pi squared r over t squared. Right now, thus far, we've dealt with the velocity. So I think that the best thing to do would be to use the v squared over r. And I will go ahead and write v final squared over r, the radius that they're actually moving in. You know, maybe I should call this angle phi sub f phi final, because it matches, you know, at that angle, they're moving at speed v final. But I won't clutter this equation. So it's understood that when the kid reaches this angle, they're moving at speed v final. What's the significance? Well, that's when they lift off. You know what? Let me get rid of the f, because this equation is true generally. Maybe I could make this a little clearer by saying, find phi final at which the kid detaches. That's detaches from the slide. Sorry about my handwriting there. Okay, so hopefully that's a little clearer. This equation would be applicable at any point before the kid lifts off the slide. So now let's evaluate at phi equals phi final. Well, what happens to this force when the kid lifts off? That's how we're going to force a solution here, by recognizing that the normal force takes on a definite value when the kid leaves the surface. That definite value is 0. So we'll set, let the normal force go to 0. And now I'm going to refer to that angle not just as phi, but phi final. Okay, so the dynamics of circular motion, this is not an energy consideration, this is F equals ma. Those dynamics stipulate that when the normal force goes to 0, the speed must have this relation to the angle. And off to the side here, there's another way to think about it. If just imagine you are this kid going down the slide. If you were to slide slower, wouldn't you feel heavier? Like the faster you push yourself down the slide, the lighter you would feel. If you're not moving at all, you know, you definitely feel the slide pushing up on your butt to support your weight. So the slower you go, the greater this would have to be. And that makes sense because the right side here has to equal the left side. If you make the right side a smaller number, this would also have to be a smaller number, which means you'd have to subtract a greater normal force. But one thing that's not possible here is for this to go negative. Like, think of it the other way. What if you wanted to go faster? The faster you go, the bigger your speed is, the greater the right side is. And that means the greater the left side would have to be. Well, how do you make the left side greater? You'd have to be subtracting a smaller and smaller number. So the faster you go, the smaller the normal force gets. If you were to go too fast, like let's say you plugged in a speed of 100 miles an hour, this would come out so big that n would have to be a negative number so that you're subtracting a negative number. And there is no way for the normal force to be negative in this case. There's no seatbelt that could force them this way. The normal force can only point outwards. So the greatest value v can take is the one that would require n to be 0. So I could say v squared over r is less than or equal to mg cos phi. I'm running out of room there. That's another way to think about it, that the speed would have to be less than or equal to that. So we're going to look at when the speed actually reaches that upper limit. And that's what I've done here. Okay, so v final squared is equal to r mg cos phi. And I made a major mistake here, didn't I? I set the sum of forces equal to an acceleration. That's bogus. It's mass times acceleration. It's really mv squared over r. Oops. So the m would cancel on both sides. Remember, we're letting n go to 0. So there really shouldn't be any m here. Pardon that indiscretion. And now we have two expressions for v final squared. One of them comes from an energy consideration, that's this one, and the other one comes from looking at the dynamics of circular motion. So conceptually, this is a challenging problem. Let me just summarize the assumptions one more time. As this person descends the slide, their potential energy is being transformed into kinetic energy in such a way that we know the square of the speed always has to depend like this on the angle and the radius. That comes from conservation of energy. But we also know that, and this is true at any angle, right? Any angle prior to them lifting off of the slide. But at the particular angle where they lift off, the normal force goes to 0, and F equals ma along the r-axis tells us this has to be true. So if they're both true, if this is v squared and this is v squared, can't we set them equal to each other? So 2rg times 1 minus cos phi final, that would have to equal rg cos phi final. And let's look at what we've got here. We've got if we distribute this, we've got a 2rg cos phi. So two of those on the left side with a minus sign, and one of them over here. This is just 1 times rg cos phi. So if we put these two on the other side, we have 3 rg cos phi, and it looks like we're left with 2rg equals 3 rg cos phi. And now we can divide out the rg. Didn't even matter. That's interesting. It doesn't matter how big the slide is. It doesn't matter if the slide is on planet Earth or Jupiter. The gravitational field is irrelevant. Divide by 3, and we've got the cosine of phi final would have to be 2/3. In other words, the angle at which they finally slip off is the arc cosine of 2/3. Of course it is. I mean, that was so obvious from the beginning, right? No. It's an interesting result. 2 divided by 3 equals, right, and I'll take the arc cosine. Okay, 48 degrees. I guess that makes sense. That's a little more than halfway. That sounds about right. I'm almost certain that as a kid, I slid off of one of these things, and that sounds about right. You do make it to about halfway or a little more before you slide off.